I'd like to welcome you all to Timber Development UK's University Design Challenge 2022, Southside Hereford. Timber Development UK is the merger of the two organisations TRADA and the Timber Trade Federation. And tonight we have 21st century timber, properties and engineered products. So what is Southside Hereford Student University Design Challenge? It's an interdisciplinary cross-university team challenge to design a community building from timber to Passivhaus standards. You have a space requirement of around 800 square metres and a budget of 1.6 million. The site for the physical building is on the boundary of two fields and is a greenfield site, formerly a park and farmland. Students and 2021 graduates from any built environment site subject can register before the 11th of February and form teams of between 4 and 8 by the 18th of February. And that's so that we can distribute software from our partners, Trimble, Passivhaus, and the AECB Carbon Light tool. And with that, I'd like to welcome this evening's speakers, Ridley, Ellis and Wojciech Plowas from Edinburgh Napier University and Jasper Meade from the PYC group. And with that, Dan, I would like to hand over to you.
Thank you very much, and hello everyone. Hopefully now you can see my slides. There's a few people in the waiting room, Tabitha, just so you know. Okay, well, hello everyone. My name is Ridley, Ellis, and I'm head of the Centre for Wood Science and Technology at Edinburgh Napier University, where I've been studying wood and wood properties for almost 20 years now, and I still haven't finished. Now, we've only got half an hour to talk about a very big and interesting topic, so I'm just going to try and focus in on the essential things that I think you need to know about wood, and maybe one or two interesting things along the way if you're lucky. So in the textbooks, you'll see that we tend to divide wood up into two groups, what we call the softwoods and the hardwoods. Now, there is a biological difference between the two, but from a materials properties point of view, the first thing that we can think about as the difference between those two is that the hardwoods tend to have these specialized cells called vessels, which are for transporting water, and the softwoods have these multi-purpose cells, which are for both strength and transportation of sap in the tree. So that means that mechanically speaking, the hardwoods can be much more varied than the softwoods. The softwoods are all very similar. But that is the simplification of the real world. And the main thing to take away from this particular slide is to understand that there's nothing particular about wood, which is about being a tree. And there's nothing about being a tree that is particularly to do with being wood. Wood has other functions for plants. And if you want to really understand what wood is for and why wood is like it is, you have to understand that it does a bunch of different things for plants, and it's not just about being strong and tall. There are other things that plants use wood for. But if we're talking about trees with secondary growth, that's trees that, unlike palm trees and bamboo, they grow outwards rather than upwards. So that you can think of them like a cone, and a cone gets wider, and by virtue of getting wider, it gets taller. So that's how trees with secondary growth, trees like spruce and oak, that's how they grow, and that's why we see in temperate climates these growth rings as the seasons change. So the thing to consider here is that when the tree is young, it's at the middle. This is the wood that it's growing when the tree is young, and this is the wood that it's growing when it's old. And the needs of the tree change over its life. So it will grow wood with different properties depending on its situation at that particular time. And once it's grown the wood, it cannot change it. So the properties of wood, they vary within the tree, and they vary for reasons to do with how the tree was growing and what the tree was interested in at that time. Now we've got two portions here. One is the sapwood and one is the heartwood. So the sapwood is the part of the tree which is, when the tree is living, is active in conducting the sap. And the heartwood is not active in conducting the sap. And in many species, this is where you find lots of additional chemicals called extractives, which, depending on the species, may add extra durability or change the color of the heartwood. Now, because of those growth rings, we have different directionality in wood as a material, and this is all to do with the direction of the mechanical properties or the direction of the stresses in the living tree. So a tree is mostly interested in being strong in the longitudinal direction, the up-down direction in the tree, because that's where most of the stress is. And it's not so interested in being strong perpendicular to those growth rings. So in this direction, this tends to be the weakest direction of the wood, because in the living tree, usually there isn't much stress in that direction, so the tree doesn't have to pay much attention to being strong in that direction. So when we're using wood, the directionality of it is a very important consideration, especially compared to other materials like steel and concrete. So why do we divide up between hardwoods and softwood? Well, it's not just about the cell structure, it's the bigger things as well. So there are historical reasons why we do it, to do with the trade history and the sources that those particular things tend to come from. But as I said, there's more diversity in the hardwoods, and that means more variability in the material properties and the different applications that you would put hardwoods in as well. But the other important thing is the typical tree form of hardwoods and softwoods. So softwoods tend to be like the Christmas tree shape. So there's a big single stem with lots of small branches that come off. And the hardwoods tend to be more branchy, bigger branches. So you'll end up with shorter logs and bigger knots in hardwoods as a rule, compared to softwoods, which would allow you to have longer logs with smaller knots in. And a bunch of other reasons why softwoods are favoured for construction timber, and because you get those nice long logs with not too many big knots in, and it's quite uniform in its material. So when you're using wood, one thing to consider is that we're not really using it according to the original manufacturer's instructions. In the living tree, the wood is completely wet. It's complete. It's not been sawn up into rectangles. So a lot of the things that we call defects in sawn timber are not defects from the tree's point of view. So the things like the knots and the slope of grain, they all make sense in the living tree or in the roundwood, but they don't make so much sense in the sawn timber state. So a lot of the things that we have to deal with using wood are from the fact that we've cut it up into rectangles and we've dried it. I've mentioned the fact that it's different in different directions, but it's also different in different places as well, related to that, what I said about trees growing wood according to their needs at that particular time. So within a piece of wood, within a log, you will get variation in the radial direction because of that change in the tree's needs over its lifespan. And also you'll have changes in the vertical direction as well, up and down the tree, depending on the wood properties that the tree needed at the base or at the top. And the big thing from an engineering point of view is this variation and uncertainty. So we don't manufacture wood, trees are making wood, or trees and foresters are making wood, but we're not directly controlling the manufacturing process like we are with other construction materials. So there is variability and there is uncertainty in there. But that's generally true of all construction materials. We never have perfect knowledge either of the material that we're dealing with or the actions on a structure. So the way in which we deal with variation and uncertainty in wood is just the same as the way that we deal with variation and uncertainty in other materials too. It's just that there's different kinds of variation and uncertainty in wood than in other materials. So when we're thinking about the value chain from tree breeding to young trees to trees being harvested to logs to the different parts of the sawmilling process before and after drying and when it gets to site, there are lots of opportunities there to consider the quality of the wood or the properties of the wood and direct the timber to the right kind of product, because you obviously want different properties if you're doing a construction. You're doing construction timber compared to paper, for example, or plywood. You want different qualities. So a lot of the work that we do is about sending wood to the right markets. But when we're talking about construction timber, we are by and large, sorry, that advanced. We are by and large talking about timber that has been sawn into rectangles, dried in the sawmill, and then graded to a construction grade within the sawmill. And then it gets to the secondary processor or the end user, and they may apply some additional sorting process depending on what they like and do not like. But essentially the stage where we're assessing that timber is suitable for construction is done in the sawmill as the last part of the process before it's sent out. So let's just step back a bit and think about how wood is made. Now, we all know that wood is made from photosynthesis. That's one of the advantages of it, that it's taking carbon dioxide out of the air and turning it into useful products and giving us oxygen that we need to breathe. But one quite amazing thing about this is that most of the carbon, hydrogen, oxygen atoms that are in wood have come from the atmosphere. So a tree is assembled from air, essentially. There's very little of that material that is coming from the ground. I know a lot of people think that if you get buried in the forest, your atoms will get turned into the tree. Well, that's not how it works. But if you go walking in the forest, you breathe out that part of you, those atoms will get turned into trees. So, okay, we know it's made from carbon, oxygen, and hydrogen, but what is that? What is the tree made of, really, apart from those atoms? Well, it's made of, whether it's hardwood or softwood, three main components. One is cellulose, one is lignin, and one is hemicellulose. Plus, we might have a bunch of other extractives in there, plus a lot of water in the living tree. Now, cellulose, you can think of that as being a bit like the steel in reinforced concrete. It imbues a lot of tension strength. Lignin, you can think of that as being like the concrete in the reinforced concrete. It provides a lot of compression strength. And the hemicellulose kind of helps to mechanically join those two things together. So trees are really clever at growing the wood, and this is all assembled at the very, very tiny scale. So within the cell walls of wood, things that you cannot see with the naked eye, we have these crystals of cellulose assembled in a particular orientation by the tree deliberately in order to control its mechanical properties. So the angle at which it lays down these cellulose microcrystals within the lignin matrix is how the tree controls its mechanical properties, that balance between strength and stiffness and density that it needs for its own interests. Now, from our point of view, when we've dried the wood, well, wood never completely loses its affinity for water. And that's down to the fact that these molecules are in the living tree always wet. And they have these OH parts, these oxygen, hydrogen parts that come off. And in the living tree, they are attracted to the water molecules, the H2O, the hydrogen bonding that you get in water that you might have learned about in school. So you get that same kind of hydrogen bonding with molecular water within the cell wall. So it's not liquid water, it's water molecules. And they kind of get in there, in between the polymers that make up the wood cell wall. So that's why when wood gets moist or dries, when the moisture content changes, that you get that shrinkage and swelling. It's atoms, molecules of water that are within that matrix of polymers within the wood cell wall. And that's as well why wood stiffness, for example, increases when you dry it out, as because you get more hydrogen bonding between the wood polymer molecules themselves rather than having water molecules in between. But for construction, we're interested in the larger scale, and the main properties that are of concern to us are the strength, the stiffness, and the density of the material. And often we're thinking about density as being where we want high density. So it's not about self-weight, it's about having sufficient density for your fastener performance or your fire performance. So it's low density that we want to avoid. There are a bunch of other things as well, like the moisture movement and the durability and the creep and appearance and so on. But I'm mostly going to talk now about strength, stiffness, density, those three core mechanical properties. And when we talk about them for construction timber, we're normally talking about the 12% moisture content, which is what wood is approximately at in a building in service. Now I'm going to talk about that in a way that also helps maybe tackle some of the misconceptions that people have about UK grown timber. So you'll often hear people say that British timber is no good for construction because it grows too quickly, meaning that it's not dense and also not strong. Because this misconception helps me to explain actually where the mechanical properties come from and how it doesn't work like this, unfortunately. Makes my life more complicated. It doesn't work like that. So the mechanical properties, yes, they do depend on the amount of cell wall material, which is another way of saying wood density. But more importantly, they depend on how that cell wall material is arranged. And remember, trees are very clever about assembling that cell wall material. So it's to do with the microstructure stuff plus the macrostructure stuff that we can see, the grain, the growth rings, and the knots, and the ratio of the different chemical components of the wood cell wall. And in softwoods in particular, they're all quite similar in that they have this, they tend to have this radial increase in density, radial increase in stiffness as the tree gets older, because a young tree, its strategy for shedding the snow and the wind is to be flexible. But an old, big, tall tree can't do that. If it leans too much, it will fall over. So it needs to be stiff and strong. So you tend to see in softwoods a trend from pith to bark of increasing density and increasing stiffness and increasing strength. And it's all cleverly to do with this microfibril angle. But essentially, what you need to know is that there is a middle part of the log which tends to have less good properties than the outer part of the log. And that middle part of the log tends to be about the first sort of 14 to 18 years worth of growth, depending on the growth situation. So when we talk about rate of growth, in the timber books, it's often talking about growth rings. So you could look at these two pieces of wood and count the growth rings, and you might think, well, one grew in 11 years and one grew in 15 years. So one of them obviously is faster grown than the other one. The one with 11 rings in is faster grown timber. But in this example, they both come from the same tree. It's really just the radial position that changed. And if you think about it, as the tree gets older, those rings get much bigger diameter. So even though they're thinner, they are much more wood. So from the forester's point of view, the tree was actually growing faster. There was more wood put on per year, even though the growth rings are smaller. So rate of growth, if you're thinking about growth rings, doesn't really tell you anything at all about the rate at which the trees grew, or very little actually. And often when we see differences in mechanical properties related to growth rings, it's actually because of radial position and radial trends in wood properties rather than the size of the growth rings themselves or the rate of growth. And this is why growth conditions have such a big impact on the mechanical properties of wood, and foresters are the ones that have the biggest influence on the timber properties, and because of that variation within within the log to do with age. Foresters can have influence through the spacing, the thinning, how long they grow the trees for, as well as having environmental influences there as well enact, like how much rainfall there is, how much wind there is, and of course the genetics and the variety and the species of the tree as well. So all these things combine, which means that you get a lot of variation. And yes, of course, different species are different, but there's actually quite a lot and often more variation within species and within species groups. And that variation acts between countries, often because of different silvicultural practices, within countries, within a forest, within a stand, between two different trees in a stand, within a tree, even within a board. And even if you have a board of timber, a sawn piece of timber, you test it in different orientations, you will get different results because of that variation within the board as well. So there are lots of variations to deal with there, and there are variations as well in the correlations between those properties. So that's what we want to deal with if we want to make sure that the timber that we put into a building is safe to use. So how do we do that? Well, it's built on this idea of characteristic values. So if you're concerned about strength, for example, it's no good to talk about mean strength, because mean doesn't tell you anything about the variation. So in the Eurocode system, in the limit states design, we have these things called characteristic values, which are usually set at the lower fifth percentile, which means that we're describing the point at which 5% of the pieces are lower and 95% of the pieces are higher. There's a statistical description that allows us then to balance the safety factors to make sure that everything is fine. So properties like strength and density, remembering that density is important for fasteners and fire performance, we are describing with the lower fifth percentile. Stiffness, we use the mean value because stiffness can be good and bad depending on the situation. So how do we grade the timber to ensure that it is good for construction? Well, there are two main systems in operation. One is called visual strength grading, and the other one is called machine strength grading. And visual strength grading, this is usually done by a person. They're looking at the things that they can measure on the outside, the things that they can see, the knots, the grain, and so on. And they're applying a set of rules from a standard. With machine grading, there is a machine and it's measuring something about the wood as it goes through, and it's making a graded decision. Now, these two grading systems are not completely separate. They are all sitting within the same system of grading within Europe. And essentially, whether it's machine grading or visual grading, you're dividing the population up according to some thresholds. So you're being able to measure something, the something on this x-axis, which is predictive of the property that you're interested in, the something on the y-axis. Now, you'd like to be able to make decisions on this axis, but you can't. You can only make decisions on the thing that you're measuring. So you make thresholds and you're sorting the timber into poor, medium, good, or whatever. You're sorting it into buckets. And you can see that in this example here, we've got some timber that we've called poor, and yes, it does have the lower properties, and we've got something that we call good, which does have the good properties. But you see there's still overlap there. There are some pieces that we've called good, which are less good than the pieces that we've called poor, right? Now, this is normal. I just want you to understand that there's still variation in there. What we're doing with grading is quantifying that variation. So there's not a huge difference in reality between, say, C16 and C24. The numbers are different, the characteristic values are different, but if you were to test a piece of C16 and a piece of C24, quite high chance that the piece of C16 is stronger, stiffer, denser than the piece of C24, just because of the variation that you still have in there. So there's a lot of mathematical calculation that's behind this, and then we end up with strength classes. Now, machine grading, you might read in books that this is done with bending machines that bend a plank of wood as it goes through. Well, we have actually a lot more different technologies in operation now. There are something like 45 different grading machines approved from use in Europe now with different systems. And the mechanical bending ones are going out. They're no longer being used very much. in the UK. Most of it is done with X-ray machines that are measuring density and the size and position of knots. But we also have a lot of acoustic-based machines as well, which are using speed of sound, essentially, to measure the stiffness of the wood. And they can operate a lot faster than the bending machines can do. This is an example for spruce, and although we do grade mostly to C16 reject with almost 100% yield, it is possible to get higher grades out there if you wanted it. There is C24 in the spruce. It might not be worth it to get it out, because maybe C16 is perfectly fine for what you want to do, and in most cases it is. So why go to that effort? But there is good quality timber in there as well. So one thing I want to really reinforce is that just because there is something that we use for grading that indicates something about the properties that matter, say strength and density, that doesn't mean that this is a fixed and causal connection, right? So we might be using ring width or knot size to make decisions about grading, but that's not because ring width and knot size determine the mechanical properties. They could both be determined by something else, how the trees grew and how they were processed, right? So this is why we have so many visual grading standards, for example, for use in different countries for different resources, is because timber grown in, say, Slovenia is different from timber grown in Scandinavia, because it's different growth conditions and different forestry. It might be the same species, but that's why we have different grading rules. Right? It's not because the knots are somehow magically different. It's that there are different ways in which those correlate with the mechanical properties. So just because a piece of wood has a lot of knots in, doesn't actually mean that it's weak. Even though knots and growth rings are used in visual grading, doesn't mean that they are defects that cause low strength. You can have a piece of wood with no visible defects in, and it's not strong. And you can have one with massive knots in, and it can be very strong, right? You'll get the slides, I guess, afterwards, and I'm not going to go through all this in detail, but it's just a main thing. I just want to make the point here that grading is not about individual properties of individual pieces, especially visual grading. You're not, when you visually grade a piece of wood, you're not saying that this particular piece of wood is this grade. You're saying that if I do this for a bunch of pieces of wood, collectively, those pieces would all have the right conditions to be called that grade. So any individual piece of wood can correctly belong to any grade. It all depends on how good its friends are. If it has a lot of good friends, it goes into a high grade. If it has a lot of bad friends, it goes into a bad grade. And we have, when we do design, secondary properties that we need, like tension strength, compression strength, shear strength, and so on. And they are all based by using conservative equations on those three mechanical properties that we're measuring when we do the grading assignments. So often the real values, if you were to test a piece of wood, the real values would be much higher than these design values. And that's because the codes have to be conservative by the time we get there. So we just have these primary properties and secondary properties. So just be aware that the primary properties are the strength, stiffness, density, and the secondary properties are everything else. And importantly, we can have two bases for grading timber, tension basis and a bending basis. If we're doing bending basis, it means we've done bending tests, and tension strength is a secondary property. If we're doing tension-based grading, we're doing tension strength testing, and bending is a secondary property. So that means you have to be very careful when you're translating between the tension grades, the T grades, and the bending grades. So don't think that you can switch between the two. Don't think that you can look at density value in the EN38. What is it? Yeah, the one with all the strength classes in. I've forgotten my numbers. But don't just assume that because you have a particular density that means that you have corresponding stiffness and strength according to the strength class definitions, because that's not what they're for. That's not how they work. Quick slide just to show the variation in the different timber quality that we expect in the UK, we do have mostly spruce. We also, though, have larch, Douglas fir and pine. And although spruce is mostly going to C16, we can get higher grades if we want from the larch and the Douglas fir and the pine. If you are specifying that, though, in your construction, just be aware that it's probably going to have to be visually graded, because even though there are machine grade settings for these other species, mostly these are produced by visual grading, which means that you can only have certain strength class choices. You don't have the full freedom of every strength class. And that's pretty much it. I think I'm almost on my time. I will provide for Tabitha to send out to all of you a copy of these slides, and I will at the end put in some bonus slides with some additional links where you can find out more information about how timber grading works and different properties of different species and what you might specify different species for. So that's it. If you've got any questions, you can ask them in the chat and we'll try and address them later. Okay, thanks very much.
Brilliant. Thank you so much, Dan. Yeah, I'm always fascinated about grading and growth of timber along with the species. Wojciech, would you like to share your screen? And as Dan said, yeah, please ask questions in the chat. If you ask them to everybody, then we all get the answers and we'll have time at the end for, you know, more questions. You're not sharing yet, Wojciech.
Yeah. How about now?
Yeah, not quite full screen yet.
No, there we go. How's that?
Okay. Perfect.
Okay, good evening all. My name is Wojciech Plowas. I'm a technical consultant at the Center for Offsite Construction. It's a center within the Edinburgh Napier University. Although my background is structural engineering, I spent now 4 years researching and developing various types of mass timber systems or engineered wood products, which is what I'm going to talk to you about today. So similar to what Dan said at the beginning of his presentation, engineered wood product, it is a vast topic. We could spend hours talking about it, different types, different manufacturing methods and so on. What I try to do with this presentation is extract the essential information that will kind of, you know, open the doors to a greater understanding of engineered wood products. So my presentation that I will give today is split in 4 sections. First, I'm going to talk about, introduce the engineered wood products. Then we're going to look at different types, the overview of engineered wood products, and a few slides about the manufacturing aspects. And finally, we're going to close off the presentation with some properties and how engineered wood products are designed. So sawn timber comes with certain limitations. So although it is a great construction material, and I devote my career to developing ways of designing and promoting timber construction, sawn timber is made of living trees, and as such, you know, the tree can only grow as tall and as large. So there are limitations, and it's a living thing. It will have defects, something Dan explained 20 minutes ago. This is why, you know, engineers and architects spend over century developing ways of laminating, of, you know, creating an engineered wood product that will overcome those limitations. Those limitations include section sizes. There are limitations. So the maximum cross-section size of sawn wood we can get in this country is 75 by 250 mil and up to 5 meters long. Even then, it's very likely that this section will suffer from convection, so we will deform, and as it dries, removes all the water from the cells, it's likely to defect. So this is really the maximum limit. Also, the availability of log size, as I mentioned, tree can only grow as high and as wide, and because it's a living thing, it has branches, it will have some defects like knots and growth ring, different orientation and so on. So for these reasons, people over centuries actually try to develop ways of overcoming these limitations by joining smaller pieces of wood together, whether it's using glue, fixings, or using moisture-controlled methods, and so on. So this is what we call an engineered wood product. Engineered wood product can be formed in a variety of forms. First, the most common way of creating an engineered wood product is that putting dry timber boards together with glue or fasteners such as dowel or nails. Engineered wood products could be formed with the veneers, and this is done by peeling logs, and which are then bonded together to produce plywood and laminated veneer lumber. Chipped to different sizes. This is to produce fiber boards, chip boards, oriented strand boards. So the sheet material that's used for timber frame construction to provide this sheer rigidity to the panel. And finally, engineered wood product can also be made by bonding or mechanically fixing together two or more of the above to form structurally efficient composite members, such as I-beams, like you can see on the bottom right of the screen. So this particular I-joist is formed from LVL flanges and OSB web in the middle. So there are certain advantages to engineered wood products. First, it's enhanced strength and stiffness. And this is because by building up the structural sections from a number of smaller elements, there are opportunities of reducing the amount of defects within the boards. So it's what we call the defect cut. So boards can be finger jointed without any defects, hence it's likely will be stronger. Increased size and scope of application, as I said. So basically, in some cases, some examples, the limitations are really how big the press is or what are the transport limitations. So mass timber product can be as large as we need them to be, as long as we can, manufacture them, handle and transport them on site. Reduce moisture content. So this is to do with the actual requirements for producing mass timber systems or engineered wood products. During production, the boards that are used are usually dried down to the required moisture content. This is to do with the required moisture content at service, which are about 12%, and also the adhesives used during production are designed in developing a way to best bond the boards that are sufficiently dried. So reduce moisture content. And that leads us to a dimensional consistency. So if mass timber systems or engineered wood products are used for construction of housing, the habitable areas, it will be heated, it will be dried, and so the service moisture content will be about 12%. So that means that timber within the engineered wood product will not expand or shrink much. And finally, there are opportunities of using the waste material. So otherwise will be thrown out. There are ways of utilizing the waste of timber for example, OSB manufacture, or creating the flakes from recycled wood. So those are the advantages of engineered wood products. And here we're gonna talk a little bit about the overview. So I had to make some hard choices in deciding what I will present today. So I've selected the 7 different types of engineered wood products, which are split in 2 groups. First group is mass timber systems. So it's a laminated veneer lumber, glue laminated timber, NLT, DOT, which is the nail laminated timber, dowel laminated timber, and finally, well-known cross laminated timber. Another group of engineered wood products I would talk about today is composite and truss systems, such as I-joist, open web joist, and truss rafters. So I prepared the slide just to give you an insight of how many different types of mass timber system are there. They can be bonded in many ways. They can be bonded parallel or perpendicular to the plane direction. Can be glued or mechanically fixed, or what some people don't know, also moisture controlled, such as dowel laminated timber, which I'm going to talk about in a few slides from now. So mass timber system is a family of solid laminate timber systems produced by connecting series of smaller timber together. And stems can be glued together, such as cross-laminated timber, or non-glued. And when the mechanical fixings are used instead, such as for nail laminated timber. So, few slides about some of the mass timber system. First one is what I want to talk about is LVL, laminated veneer lumber. So this is a structural member manufactured by bonding together thin vertical softwood veneers. Veneers are usually 3 to 4 millimeters thick and are peeled off good quality logs and laminated vertically. In production, veneers are orientated with their grain parallel to the longitudinal axis of the section. In some cases, however, the cross grain veneers are incorporated to improve dimensional stability. You know, the timber will expand in different rate in different directions. So incorporating this cross lamella will actually help with the dimensional stability. In terms of applications, so LVL is used mostly where the structural member of higher strength is required. So this is for heavily load-bearing structures, such as you see here the truss with the large spans. This is where the high stress occurs and the load-bearing, higher load-bearing is required. It can be used as panels, beams, and columns. And for reference, there is the standard BSEN 14374 that outlines the requirements of laminated veneer lumber. Next on the list is GLT. Probably everyone heard about glue lam, so I've information. So this is a structural member made by gluing together a number of graded timber laminations with their grain parallel to the longitudinal axis of the section, as you can see on figure 9 here. GLT can be straight or curved, horizontally or vertically laminated. Also can be used to create a variety of structural forms. Laminations are typically, or the boards are typically 25 to 45 millimeter thick. So in terms of the structural consideration, GLT has a high strength to weight ratio and achieves high standard of architectural finish. I'm sure you all seen structures which utilize the large beams of glue lam. So the end effect is really pleasing to the eye. Not only, I mean, when I go to Botanic Garden, I see, like, you know, the structural member, but you know, it's looking very nice when it's put together. In terms of the final size of the element is dictated by overall section size and the grade of timber used. So here is an example, some examples of how GLT was used. So as I mentioned, large structural end can be used for post and beams constructions, in some cases bridges, heavy timber framing elements, as well as arch structural shapes. In terms of connections, these are usually made with bolts and plates, as you can see in figure 11 here. And the product standard, BSEN 14080. Again, it outlines all requirements for glue laminated timber, starting from its properties, how to obtain those properties, what timber is allowed to be used, what adhesives should be used, what are the board characteristics, and you know, all sort of information that you can find in the standard. There are two different types of glue laminated timber from structural engineering point of view. Two different types of glue lam. First one, what we call is a homogeneous glue laminated timber. This is where all boards within its cross section are made from the same strength class. Another type of glue lam is combined glue laminated timber. This is, in my opinion, better use of material, especially when it's used when the glue lam is used for beam application. So what happens in here is that higher strength class is positioned at the top and bottom of the section. This is where the highest bending stress occurs within the section, whilst in the central part of the beam is a lower strength class of timber, as there is very little stress going on in this section of the cross section of the glue lam. Nail and double laminated timber, those are fabricated from softwood timber lamellas stuck in one plane and connected either with nails for NLT or hardwood timber dowels. The thing with the DOT is that moisture controlled solid laminated timber system. What that means is that during the manufacture, the dowels, which are usually hardwood beech dowels, are dried down, the moisture content lower than those of the lamellas, to about 6 or 5% moisture content. And then in service, they gather up moisture content and expand slightly. But what happens then is that they lock the system together. So in both of those cases, the panels can be manufactured flatwise orientation to form slabs for floors, or edgewise to form beams. In terms of the structural considerations, both NLT and CLT have similar attributes to cross-laminated timber, can form self-supporting floor, roof, walls, slabs. It has a potential for long spans and hybrid high-rise constructions. Connections are usually made with bolts, plates, or angle brackets. And finally, we have cross-laminated timber. This is a structural product, engineered wood product, with a minimum of 3 cross-bonded layers. Timber layers are glued together in a press, which applies the pressure over the entire surface of the panel. CLT typically have odd numbers of layers, from 3 up to 9. Those layers are usually arranged symmetrically around the middle layer. What that means also is that, with the CLT, all adjacent layers have their grain direction at the right angle to one another, and cross-laminated timber. Structural considerations. So CLT has a large axial and flexible load-bearing capacity when used for wall and slab, high in-plane shear when used for shear walls, and superior acoustic and thermal properties. Here are some definitions used commonly when talking about cross-laminated timber. We have a side faces and narrow faces. In terms of the layers, we have a top, cross, and middle layer. In terms of the dimensions, those are dictated by the size of the press, again, whether handling capacity and transportation. But most commonly, the maximum length of CLT is 16 meters, can go up to 30 meters, but this is on special order and will cost premium. In terms of the width, the maximum width of the CLT is 3 meters, and maximum thickness is 0.3 meters, so 300 millimeters. Can go up to 0.5 or half a meter, but again, this is on special order. It's possible, but not very common. According to CLT standard, the thickness of a lamella should be between 6 to 45 millimeter, although typically the lamellas are 20, 30, or 40 millimeter thick. In terms of the width, it can be anything anywhere from 40 to 300 millimeters, although there is a recommendation to keep the ratio of width to thickness to below 4. It's to deal with the kind of failure that could occur when subjected to high bending stresses. When the rolling shear failure, when the cross lamellas fail along the rings of the growth rings of the timber. So it's always safer to keep the width to thickness ratio to less than 4. So in terms of the different types of CLT, it's really almost infinite possibilities to create layups of CLT. The most common ones are what we call the minimum, so three-layer CLT, usually for non-load bearing situations or for wall constructions. CLT is good in compression. We have a standard, which is 5-ply CLT, used usually for walls, floors, and roofs. Maximum span, again, this depends on the species and strength grades of the boards used within the layup, but it's usually around 5 to 6 meters maximum span. And we can go quite deep if you need to be. So maximum up to 11 layers. I mean, it's possible. I haven't seen it personally, but I know it's possible. There were some very big sections available as well. when talking about CLT and GLT, I mean, it's worth mentioning that, you know, when the desirable span, clear span, it cannot be met. So in this case, we can prop it. We can create the rib floor, where we can combine the CLT slab with, for example, glue laminated beam or I-beam or steel beam to create the rib floor. We can use it to create a box beam. Again, this is if we need a higher or longer spans are required. Or finally, we can also create a composite floor with concrete or wood-based panels, such as plywood or LVL. Here is an example of actually all mass timber systems. I can see 4. So if the picture you see here, it's a modular unit constructed from 4 different mass timber products. They were all, in all cases, homegrown mass timbers. On the walls on this picture are made out of CLT. The ceiling is nail laminated timber, and the beams in the middle of this modular unit are glue laminated timber. As I mentioned before, CLT has a capacity to provide a self-supporting floor, roof, and wall slabs. It could be used for multi-story residential, schools, sports halls. Also, there are opportunities for bridge and hybrid type construction, although there is a recommendation that laminated timber, like cross-laminated timber, shouldn't be used up to service class 2, so in sheltered conditions and heated spaces. And here is a reference to the product standard, BSEN 60351, with all the requirements, containing all the requirements for cross-laminated timber. So just to summarize the applications of mass timber systems. So glue laminated timber and laminated veneer lumber can be used for post and beam construction, featured trusses, or curved structural shapes. Cross-laminated timber, as well as nail and double laminated timber, can form floor, walls, and roofs. In terms of the structure, not first the dimensions. So as I said, the maximum sizes are dictated by the size of press, handling capacity, and the transportation. In terms of, as I said, the sawn wood, sawn timber is could be up to 5.4 meter long, 75 millimeter wide, and 250 millimeter deep. As we can start, you can go and have a look at those other numbers. So LVL, for example, can be up to 20 meters long and be up to 2.5 meter deep. With glue lam, I couldn't find a limit for length. It can be as long as need be, and I've seen some very, very long presses. And both glue lam and CLT can also be finger jointed, as in the whole panel can be finger jointed. So there are very little limitation when it comes to sizes of mass timber. In terms of the properties, so I've got 3 graphs here. The first one on the left is the stiffness. The one in the middle is the bending strength, and the one on the right is the characteristic density of 3 different mass timber, and this is compared to the properties of C16 strength class. So as I've mentioned, LVL in all cases is the stiffest and the strongest of all, and that's why it's used for the heavy stress situations where the stress is quite high when the loading is high. And after that is a glue laminated timber and C24 and C16 strength class of sawn timber. So now we're moving into a composite engineered wood product. The first one on the list is I-joist. So I-joist is manufactured with flanges made out of softwood or LVL, and has a glued thin webs generally made from OSB, fiberboard, or plywood. I-joist can be used to resist either flexural or axial loads, or combination of both, which means they can be used as beams to resist the bending stresses, or can be used as studs to resist compressive forces. Available section sizes range from around 200 millimeter to up to 500 millimeter deep, which allows to introduce a lot of insulation in between, which I will talk about later in this presentation. In terms of the application, I-joists are usually used for floors most commonly. However, they also could be used as a roof joists, ceilings, load-bearing studs, and for prefabricated cassette floors. Open web joist, this is slightly more premium engineered wood product. This is basically a shallow parallel core truss manufactured using similar techniques to that used for roof trusses. Just in this case, we have softwood cords on the top and bottom that are joined with the metal webs that are forming the triangulation and truss system. The strength class of timber used for open web joist manufacture is usually C27 or TR26, which is a unique strength class made for truss rafters. Metal webs are typically profiled from 1 mm galvanized light gauge steel. So as you see on the figure, as of the open web joists are often preferred to I-joist if the budget allows, as they allow for services and structural element to pass through them without jeopardizing the load-bearing capacity of the joist. So this particular engineered wood product is usually used for roof and floor joist elements, ceilings, and prefabricated cassette floors. And the last one, the last engineered wood product that I would talk about today is a truss rafter. You can see the two pictures here. So we've got truss rafters on the top right, and on the bottom we've got modular roof with roof trusses. Truss rafters built in, where the trusses were used to build this in. So what is truss? Truss rafters are now specified for majority of domestic roofs constructed in the UK. The truss rafter is an individually designed component engineered to provide structural frame to support roof or similar structure. It's prefabricated from high quality stress graded timber and joined with steel nail plate fasteners. The advantages of truss rafters are this: flexible and practical, available in many shapes and form. It's economic, as it uses up to 40% less timber than traditionally formed roof. Reduced labor cost. This is to do with the amount of prefabrication. And it's very quick to erect, especially for the trained joiners. You can put the roof up in a day or two. And so that's the third part of my presentation. That's manufacturing aspects of engineered wood products. So generally, the way I like to describe the manufacturing of mass timber is in 3 stages. So the 3 groups of activities that need to take place when manufacturing any wood product or mass timber systems. First of all, is the log processing, and so sewing wood into boards, which then they are either graded before or after they are dried to sufficiently low moisture content, which is usually about 12%. Once sorted, dried, and graded, the boards are then prepped for the glue application and pressing operations. And by that, what I mean is that they are cut to size, they are finger jointed, sometimes the defect cut, and finally planed to the required thickness. The second group of activities is adhesive application. This is quite self-explanatory, depending on different mass timber product like glulam or CLT. There's different glue rate application. There are different types of adhesives. There are 3 groups of adhesives that are used for manufacturing of mass timber. The most common ones are the PUR or MUF types of adhesives. And the third group of activities associated with the manufacturing of mass timber systems is pressing, nailing, doubling, depending on what mass timber product you manufacture. In terms of the production requirements, I listed several requirements specific to CLT, although I know that glue laminated timber have very similar requirements, and same goes to NLT and GLT and then DLT, sorry. So in terms of the production requirements and the quality assurance and assurance of consistency of performance of the products manufactured, there are certain requirements that have to be met during the production. One of them is the air temperature. So during the production, the facilities shall be at least 15 degrees centigrade or 18 during curing of the glue lines. This is to do with the speed of curing, how much time the glue needs to cure properly. Relative humidity of the production plant should be between 40 and 75%. At assembly, the moisture content of the board shall be between 6 and 15%. Usually it's somewhere in between, about 11 or 12%. In all cases, lamination should be planed before bonding, and planing shall be carried out not more than 24 hours before the bonding. And the last section of my presentation is the properties and some design aspects of engineered wood products. So I thought I'm going to start with the information, or where to find information about the engineered wood products. You might want to specify this design and you want to use one of the engineered wood products. So where do you look for information? So if the product is available on the market and is certified, it has to have what we call a European technical assessment or declaration of performance, which will outline the technical properties, the mechanical properties, dimension specification, and intended use and working life of the product. So whether it's a CLT, laminated timber, and so on, all you have to do is find a manufacturer who is most likely to carry out the suitable test work to allow him to declare the properties of the product. And that's where you're going to look for the information that will help you to specify the engineered wood product you want to use in your design. In terms of the construction, so here is an example of a modular unit or two modular units, one stacked on top of another. This particular modular unit utilizes all three mass timber systems. So we can see here the ceilings were formed from nail laminated timber, the walls from CLT, and floors from glue laminated timber joined vertically to form slabs. And some connections examples that were utilized for this particular project. As you can see, in most cases, the screws were used. This is to allow for easy assembly and disassembly of the system. And so what we have here is the standard, I guess, or typical cross section of the CLT. Maybe not typical, because in most cases CLT is exposed. But what I want to show here that how the building could be constructed, walls could be constructed using CLT. So what we have here is the service void from the inside, then the load-bearing CLT element. You have to use the insulation, suitable amount of insulation to satisfy the building regulations. On top of that, you will have a breather membrane, same one as used for the timber frame construction. And finally, you have your cladding. In terms of the I-joist, so I might have mentioned that in my previous slide. So I-joist becoming more and more popular, used as a studs. It's to do with the amount of insulation you can put in between or within. So they use relatively little volume of timber. If you were to use a standard cross section of sawn timber, that would be pricey, and you would use a lot of material. If you need to accommodate a lot of insulation, you want to increase the depth of your stud. The sawn timber might not be the most economical option, so that's why the studs are preferred often. Another thing is that you see this thin part of the section where the OSB is, the web. that allows to put the insulation in between, hence minimizing the cold bridging. So Tabitha will share this presentation with you. I hope you find it useful. I've included some references if you wanna have a look. They should be all available, and I'm sure you find it useful. Thank you for your attention.
Thank you, Wojciech. Yeah, no, actually fascinating, and the way we've engineered timber and extended the products and the range in these last sort of 50 years is quite incredible. I know there have been a couple of questions in the chat, but I'd like to now hand over to Jasper Meade. And Jasper, I know you've used most of these products within your projects.
Yes, hello. You see my screen all right?
Not yet.
Not yet. There we go.
Yeah, that's perfect.
Good. Yes, so we certainly have, and great to hear those presentations, and really made me realize why we use wood and why I love wood so much, and how it's such a great material to work with. So I'm going to talk about how it's developed with us, how they introduced my company a little bit, but how timber systems have developed and how we construct with them, and the offsite manufacturing, and follow up with some projects, some specific projects that we've worked on. So our company's got a history of building with timber, working post and beam originally, and moving on to softwood, and developing super insulated systems, and welcoming Passivhaus when it came along in 2008, working very closely with Passivhaus designers, builders, and over the last 10 years, 13 years, 14 years now with Passivhaus, we've come a long way in the UK with Passivhaus, and some great projects have been realized. So we've got our own facilities where we do offsite manufacturing, and it's a portal steel frame, I'm afraid to say, but we've used timber everywhere else in our building. And the first building that we built in our workshop was our offices, which we designed and built to Passivhaus standards. There we used a combination of glulam, element of CLT, box beams, and I-beam construction. So the development of timber frame throughout the UK and started obviously very early on, and in fact we often get challenged by clients, builders who would like to see their building built traditionally, and they think of traditional as being brick and block, and we certainly argue the case that timber is by far the most traditional material to build out of, and we use traditional materials in a modern way. So that started with post and beam construction, certainly no thought about insulation, just weather protection and shelter. And then that's moved on. I'm going to race through these, plenty of time for questions afterwards, hopefully, and please contact me separately afterwards if you need any more information. But showing this particular slide, I like to show it because, again, a frequent question we get asked is, how long will a timber frame building last? And we would argue, detailed right, it will last indefinitely. And this particular building shows testament to that. It was a tin chapel. We've got quite a lot around our area, and North Wales and Shropshire area. And having taken on this building to convert it from a chapel to a house, we were really surprised to see how solid the structure was underneath the tin. We took off the tin to insulate it and increase the insulation depth, but really the timber structure was incredibly solid. It only failed at various points where water had been left ingress, but generally very, very good condition after many, many years of service. So mainstream construction in the UK was with single studs, 90mm being the first really, but that soon got lifted to 140mm when insulation levels increased. But when you look at single stud construction, you've got pairs of studs, lintels, you've actually got a lot of solid timber right through the whole wall structure. And by default, you're allowed to use a figure of 15% when working out your timber frame, timber fraction in your structure. But if you do a true calculation, you can find it can be as much as 25%, which is essentially a large area of a building which is uninsulated. So we would look at ways of mitigating that, and cross sections of secondary timber, sort of creating a lattice of timber, if you like, and cutting down the coal bridging points, increasing the insulation depth, using smaller sections of solid stud. But this was quite a fiddly way of doing it, tricky to insulate. Even though with blown fiber, it still can be tricky to insulate. So we looked at other methods, and timber joists, posi joists, or metal web joists have been used for wall structures and roof structures, but the problems with them is you do get an element of coal bridging through the steelwork, albeit it's very thin, but steel is a very good conductor of heat, so therefore doesn't perform so well, certainly not for passive house structures. So twin frame, that twin frame Larsen truss system has been widely used. A lot of very successful passive house schemes have been completed using these systems. So essentially you've got two layers, can be joined as such as the Larsen truss with a fin of OSB, or separated out but joined at certain points such as floor levels. The great thing about this is you can have one section which is your structural element. That's typically on a passive house it would be the inner wall, so that's carrying your loading, and then your outer section is going to increase your thickness levels and cut down that coal bridging. But other methods which we work with in the main is I-beams. So I won't talk about those too much because Wojciech described that very well. I-beams, with your flange and your web, you can do some great big spans and cut down your coal bridging element dramatically using this. And this is a typical detail. Give you an example of a closed panel I-beam structure with a service zone on the inside, and as you can see, you can maximize your insulation levels to whatever is required with this system. We're working with offsite manufacturing. We've done a lot of stick building, on-site construction, and we've now moved forwards in the last 5 years to offsite manufacturing. And indeed, the UK is really moving fastly towards doing as much offsite manufacturing as possible. And I'm just going to talk through how this works and how we work with it with the timber frame systems. So modern methods of construction, there's all these key reasons why it certainly is a better way to build, improving efficiency, quality control sections, and your environmental benefits are such that you can optimize your timber and save on waste, and certainly recycle and control that aspect of it in a much better, high performing way. Modern methods constructions, there's a sort of standardized category definition of these. So one being volumetric, and that would be with perhaps, I mean, we've worked with CLT on projects where you create essentially boxes which then get pieced together, widely used by the likes of for student accommodation, hotel accommodation, such as Travelodge, Premier Inn type buildings. They really lend themselves to volumetric. And our preferred section is with 2D, so category 2, which is panelized, can be open, but typically we work with closed panels, pre-insulated. And then category 3, which is your post and beam. Although we've worked a lot with post and beam we treat now as a sort of secondary element to increase the structural potential of our builds. So we might use glulam beams for ridge support, post beams, floor spans, etc. I'm going to show you a little video. This is explains really well how we work and how timber frame manufacturing happens in our little world.
Welcome to PYC, the house building factory. We're going to have a one-shot tour through our passive house offices and the workshop. So running down the corridor, we go into the meeting room here on the right. This is where we'll have client meetings, CPD presentations to architects, team meetings, etc. You can see we've featured timber, Tianos posts and beams for supporting, birch face ply, lighting trays, poplar tables, etc. Running through back into the hallway here, glulam, tongue and groove glulam, past the dining room, up the stairwell where we've used tongue and groove glulam for the treads as well as the risers on the stairs. Copper piping handrail. Now up into the main office. MVHR pipework along the perimeters there. Sound cell on the ceiling to cut down the sound. There's Ben, project manager, behind the screens there, Molly and Leah. We're going to head out through to the workshop. On the walls we've used 7 kilometers of Douglas fir. There's the sign, PYC sign and logo made from Meadite Extreme. And around to the end of the building where the main entrance is, we've got a 5-meter doorway which enables us to get Arctics in and out for moving large pods, offloading packs of materials should we need to. We buy the I-beams in 13-meter packs and they then get rolled onto the cutting table. Here using the Tiger Stop system, automatic push stop. Carl is cutting and prepping sections of I-beams for panels. They'll get stacked, ready to go onto the tables for forming into the panels. Here's one that Solly's working on. A roof panel with a skylight opening in it. He's drilling holes in the ends so that we can inject warm cell into each individual panel. And then on the next table here, getting ready for boarding, lining up the noggins. There's Tim and Brooke. And then across over on this section, Bobby and Matt are moving a panel which is finished. You can see the service zone from the underside there. That's put onto the stack. With Ryland here, he's going to be injecting the warm cell with the Lance system, so dense packed warm cell down each void. Once all the panels are completed, they get stacked, wrapped with polythene, so they're fully weather protected. They then get stored outside. Just around the corner here, we've got a couple of houses stacked and ready for delivery. All the polythene gets brought back to site after it's taken off and it's recycled. There's the stacks with warm cell and then our storage racks and bays for the boards and beams. And Dan here is loading panels onto a lorry for a job up in London. He's stacking in an order so that when they arrive to site, they get offloaded in a sequence that suits the craneage and fitted on site. Hope you enjoyed the visit. Look forward to meeting you sometime soon.
So I hope that gives you a good idea of how our manufacturing process works. And I'm just going to talk a bit about the design part, and very important to try and get early engagement as much as possible. In design, it can be quite a long process. We tend to say about 12 weeks from design through to manufacturing. And working on a fabric first emphasis, we will pretty much always use PHPP, the Passivhaus planning package, to design the buildings to perform. And Passivhaus, just for those who are unfamiliar with Passivhaus, it's only short, I promise you, 90 seconds this one. Gives you a really brief idea of what Passivhaus is about.
Passivhaus explained in 90 seconds. Does your house have a heater in the basement or maybe a fireplace? Probably also a central air conditioner or maybe a window unit. Did you ever wonder if it was necessary? In 1991, a physicist in Austria, Dr. Feist, built the first passive house. Here's what he did. 1. Proper insulation. It's just like wearing the right winter jacket. It also doesn't need a heater. 2. No air leakages. There should be no holes, small or large, to let hot air out of the house. 3. No thermal bridges. A thermal bridge is like a road for heating energy in which warmth can travel right through your walls. As a matter of fact, most of our houses have thermal highways in our walls where heat can easily travel to the outside. Plus, the house needs proper windows most of the time with triple pane glass. It needs to be oriented properly so the sun can heat it in the winter and shade is provided in the summer. And it uses an HRV, a device that provides the inside with fresh air without letting the heat out. Add all these things up, and it turns out your house doesn't need a heater or air conditioner. So where does the heat come from? A passive house needs 90% less energy, and that can easily be supplied by your body heat, the sun, your appliances, light bulbs, and even your TV. This saves you a lot of money on your heating bill and helps preserve the environment.
So that's why we build to Passivhaus standards. And these are some key points which you need to look at for designing and achieving that standard. So form factor, a simple basic structure. If you start at that point and then enhance your building from there, it enables you to get the best performance out of the volume of the building related to your surface area of the perimeter. Orientation, solar gain is a fantastic free energy source, of course, so trying to optimize the building so that you get the best value from that positioning. Heating and cooling, so not really talking about how it's going to be heated, but just understanding the occupancy of the building and what requirements there will be. So busy buildings such as the veterinary practice that we're talking about in a bit need heating, but certainly cooling can be an issue. So overheating needs to be addressed, and Passivhaus planning package will sort that out. And the ventilation, that can help. So MVHR, but also that purge option which you can get through high level glazing, window openings to get rapid purging should that need arise. From a construction point of view, we've got these key points to look at, and coal bridging, we work with an I-beam or a twin frame system. That's going to give you the wall performance. You can fully pack that insulation into the thicker structure. So varying from sort of 200 mil upwards typically. Air tightness, then using boards, with some great manufactured boards that we use from Meade, and so airtight boards and breathable boards, and some we use wood fiber boards as well for flange filling in I-beams, so where you're joining panels, for instance. And then wind tightness externally, you've got to be really careful about the detailing and materials that you use to ensure that your building's wind tight, so prevents any wind blowing in and cooling. And the triple glazed windows, and again the MVHR system. So early engagement, really important. So value engineering, which often happens on buildings, but at a later stage, typically at a later stage, post-tender. By then it's actually a bit too late, really, because you've designed the building. So look at it early and try and really work out what the budget is, what the design requirements are, to understand and get all those details sorted out at an early stage, rather than, oh my God, we need to save some money here, let's chop that section off or cut the insulation down, and all sorts of terrible things can happen at that stage. Part of what we would use, so various software for U-value calculations, but PHPP in the main for fully analyzing the whole building performance. Briefly, this is showing you a section of the buildings, I-beams here, all twin frames, and showing the closed panel, service zone. Service zone's great use for prevention of cutting through, causing air leaks or vapor control leaks. Modeling, so we would typically model in 3D and bring forward through with the engineers to groundworks to work out what structures required, and then working with elements of glue lams. So we would use glue lams perhaps at the bases of rafters on ridges, and then larger glue lams for beam supports. Occasionally we'd use CLT. CLT is a great material for giving solid structures, such as where we've used them in instance apart from volumetric, but for floors where you've got overhanging floors and you need to have that strength, and avoiding using steelwork in it. just showing part of the 3D modeling here, where you're using a ventilation system, NVHR system, so importing the two 3D models to avoid clashes, such as trying to poke a pipe through a large beam. Pretty difficult. Fire risk, I'm not going to go into this in any kind of depth at all, but it's proven to be a big issue, yet it's something we shouldn't be frightened of. And in fact, with timber, you can get some great benefits. We've done some fire tests recently with a twin wall system, an I-beam system, and had some fantastic results in performance results. So 89 minutes on a 240 mil structure with single layer of plasterboard. So really, really good achievements. Key areas of detailing. So this is using an I-beam system or a Larsen truss system, where you've got a cantilever over a raft foundation to maintain that cozy duvet layer wrapping around, and producing the panel drawings through to the manufacturing process, insulating, and there's your end product to the walls. Racing through this so I can time for Tabitha to ask some questions. Then the manufacturing, the on-site process, craning to site, very rapid. When you've got an off-site panel delivered to site, in a week you can have a 3-bedroom, 4-bedroom house up, fully up and weather protected, even in tight awkward spaces such as this particular one on a tight street in London. I'm going to talk a little bit about some projects now. So this is the Bryn Veterinary Centre in Cheshire, and this was the first passive house veterinary practice in the UK, which we did the design work on. It was built using an I-beam twin frame system using cellulose fibre, dense packed cellulose fibre, and there's some key challenges on this. So you've got high occupancy, sometimes really smelly times, as you can imagine, with lots of pets in there. So ventilation and purging of that was key to this, one big part. So stripping back to the structure, looking at the detailing, where we've got supports of, again, glulam beams for ridges and floor beams, and wood fiber boards externally. So wood fiber board can add great thickness to the insulation layer, help cut down cold bridging, but also can be used as a base layer for render. So in this instance, it was used as a base layer externally for rendering to directly, and also running around perimeter of windows to help mitigate cold bridging at that point. So that's the finished building, render through to finish. And so other projects, this is the first passive house offices in the UK, in Mahuntliffe. There's some great university buildings, in this particular one in Norwich. Lots of schools, passive house, twin frame, dense pack with cellulose fibre, and in some, this is a fully suspended on piles, so fully timber frame building in Surrey. And then some massive schemes such as this particular one, where it was designed by Michael Riches, built in by Norwich Council. There we go, wrapping up quickly, Tabitha. Thank you.
Brilliant, thank you, Jasper. I think you covered, yeah, all the different products and all the different methods of bringing them together. And obviously, again, bringing in Passive House and why it is so important, and why we need to reduce energy first and foremost, and then use low embodied carbon products. So while people are getting ready to formulate their questions, I'm quite happy that everybody turns their camera on and asks them directly by just putting their hand up. I'm just going to share my screen. So I want to say just a huge thank you to Dan Ridley, Ellis, Wojciech, Plowas and Jasper Meade. If you'd like to join us on Thursday, you'll hear from Robert Hairstands, who will be hosting, which is nice to have a night off. Andrew Livingstone, Gavin Knowles, Shingi Torreira and Grigor Mitchell, all more about timber connections for system performance. And if you want to come and join us on a virtual pub on Friday, please do. We'd like to thank all our sponsors. We could not put this on without sponsors. And this webinar is being provided alongside our Southside Hereford University Design Challenge for students. And please spread the word widely. We would love more students and recent graduates to get involved. So can I open the floor to questions? Has anybody got a burning question? I know there was one about hardwoods. We had all about softwoods. I don't know if Danny, if that's one for you. Looking now to
yeah, I must have missed that. I'm just scanning down. Wojciech answered that partly.
Oh, brilliant.
So yeah, the question is what potential there is for the increased use of hardwoods in engineered timber and I guess construction products. Certainly there is an ambition in England to try and get more hardwoods into construction products just to match up their forestry objectives with timber in construction. And there's probably quite a big potential, and I mean it already happens with products like particle board, which includes a lot of hardwood and recovered wood. It's a very nice green product. It doesn't get as much praise as it should. But yes, I think with a bit of work, there's a lot of potential for CLT-like products, laminated, things like glue lam with hardwoods, especially with some interesting developments in the faster grown hardwoods, the lighter weight stuff as well. Poplar, aspen. There's been quite a bit of work done on tulip wood that I'm sure you've all seen in the media. But yes, how to? It's a trickier question to ask how to get hardwoods that are from forests that have not been managed for timber as the main objective. That's a little more complicated. It's more varied because of the way it's been grown. But I mean, I'm sure wood fiber insulation, you know, all sorts of products that it could potentially be.
So OSB has never been made out of hardwood, has it, or has it?
I don't know enough about OSB and the limitations. I'm pretty sure that people must have done research projects on it. I imagine there's been OSB made with all sorts of things. But it's, I mean, it's made in the UK, it's made from the kind of logs that don't go into other products, because there are a lot of, I mean, forestry is a bit like butchery in that you can't all have steak. You've got to have the other cuts as well, and the other cuts have got to go into the other market. So you can't just have one thing. You've got to have small logs in the markets for those.
I was told by the sawmilling industry, it's like your core products and your co-products. So their core products was the sawn timber out of the logs, and all the co-products that go around that, even to the falling boards and into the fencing and into the chip and into the bark. And yeah,
I guess like what I wanted to say is the fact that we don't use, as far as we know in this conversation, we don't use much hardwoods in OSB could be because there's plenty of softwood, and that's a good use for the softwood. Might be nothing to do with the technical limitations. But I don't know. Someone should Google that and tell us.
No, thanks, Dan. So has anybody got any questions? I know there was so much information you put out there, and I think you answered. We've got one here. Jasper, could you expand on how cellulose insulation material is manufactured?
Yeah, it's second part of my presentation. I was running on that one without having to add too much about cellulose. Cellulose fiber insulation is made from recycled newspaper, with the addition of salts, mineral salts, to help formulate it and make it fire retardant, rot resistant, and insect resistant. Widely used in the UK, we probably use about 1,500 tons a year. In Europe, 250,000 tons. In the States, probably 1.5 million tons. So very much a mainstream insulation elsewhere in the world. Still a bit niche here in the UK, although that's changing. Quite a lot to it, but I can do that another time. Hope that helps, Neil.
No, yeah, thank you. He said, yeah, thank you for that. So if there's no further questions from our audience, I'd like to say, gentlemen, thank you very much. And I'm going to stop the recording now.